Hi everyone. So in the previous video I ended by discussing how water dissolves a ionic compound like sodium chloride, table salt, and you remember from that video that basically water makes electrostatic interactions, positive negative charges interactions with the ions in the sodium chloride, and thus pulling each of the ions apart, and eventually the entire salt structure uh, crumbles apart because of interactions with multiple water molecules. For a covalent molecule which doesn't form ions, it's basically the same concept, except that for a covalent molecule, it'll be the entire unit of the covalent molecule that gets pulled apart. So here's an example of sugar, table sugar, which is a covalent molecule, C12H22O11. So each of the hexagon that's drawn here represents a sugar particle. And sugar is not an ionic compound, so the sugar particle is just one unit, and it makes interactions with other sugar particles in the solid. So this is a solid structure of sugar, the sugar crystals, which is the sugar that you have at home. And if you, of course, if you know, you take this and you put it in, let's say, a cup full of water, and you start mixing, then the sugar will dissolve. And so how does it dissolve? It works the same way as the ionic compound, the table salt. In this case, you have these sugar molecules that are initially packed together like this in the solid, and then the water molecule comes along, and then it starts to pull apart the sugar. And the interaction is an electrostatic interaction. The difference is that water is a polar covalent molecule, and sugar is also a polar covalent molecule. So similar to sugar, similar to water, sugar has parts of it that are partially positive and parts of it that are partially negative, and they make appropriate electrostatic attractions with the water molecules surrounding them. So in this case, you have several water molecules surrounding one sugar particle, and then you have, again, several other ones surrounding this one. So it's the same idea like the salt, except that in sugar, which is a covalent molecule, there are no ions, right? In salt, you'll have different ions that are making interaction with the water. Okay, this is an important slide here because it shows you how we write species when water is present, okay? So when you have a solute that's dissolved in water, we would write it, there are two ways of writing it. First, we start by writing the solute itself, in this case the ionic compound, sodium chloride, and it's a solid to start with. So we'll start NaCl solid, and then we put an arrow and then water liquid on top of it, which just means that we're putting the sodium chloride into water. Water is present in a huge amount. There's no real chemical reaction that occurs here per se. There's, you can call it a dissolution reaction, but it's not chemical reaction the way that we think about it. But what happens, of course, is once you put the sodium chloride solid into water, the sodium chloride now breaks apart into its ion. So it really has this form right here. However, it's common that people would write the sodium chloride as sodium chloride aqueous, which basically implies that it's present in this form, sodium plus and chloride minus, and both in aqueous form, meaning that they're surrounded by water molecules, each ion. But sometimes this is written because of importance in stoichiometric calculation, because a lot of times easier if you think of this as a unit when you're making your stoichiometric calculation. So this is what we refer to as a formula unit. It basically doesn't really exist as this species in water. It really exists as the ions, but sometimes it's written as this in equations because there's certain calculations where it makes more sense to write the sodium chloride as one unit, even though we know it doesn't exist as that in reality. Okay? Now, what about a covalent compound? It's the same. Here you have methanol, CH3OH, which exists as a liquid. If you put water in it, you can mix the two together, it becomes a homogeneous solution. Then what you write afterwards is just CH3OH aqueous. Now, of course, for a covalent compound, you don't form ions, so you never write it into this form. Okay? All right. Another term you'll hear often is that when we say ionic compounds, it goes from this to the ions. We often say that they dissociate, so they break apart. upon mixing with water. So dissociate is a word that you want to keep in your vocabulary, because that's one of the things that we would say when an ionic solute is dissolved in water. So a long time ago, when people were still studying electricity, they realized that one of the things that you can use to differentiate the different types of solutes in an aqueous solution is by measuring its electrical conductance. So what is electrical conductance? It's just a measure of the number of electrical charges that pass through a medium, such as your your aqueous solution in this case. So if your aqueous solution, so here's a little picture here, maybe a little hard to see, but I'm going to blow it up here a little bit more. There's really three different setups here. You might be a little harder to see because this one is so bright. But basically, if you notice carefully here, there's basically two different what we call electrodes that are being placed into this solution. And there's three different solutions. There's three different beakers right here. This is beaker 1, this is beaker 2, and this is beaker 3. And these electrodes are connected to a light bulb. This is one light bulb which is clearly shining very brightly. This is another light bulb which is shining but not so brightly. It might be hard to see because this one is so bright, but this one actually shows a little bit of light, but it's hard, it's not as bright obviously as this one. And the last light bulb is this one, and that one completely doesn't show any light whatsoever. So it turns out that different types of solutions conduct different amounts of electricity. So this one conducts a lot of electricity, so you see this very bright light bulb. This one conducts only a small amount of electricity, electrical charges, so you see only a little bit of light. And this one conducts nothing, so you see no electricity here, no light bulb. So we can define or differentiate among different aqueous species by determining how much electricity passed through the solution. Now, one thing that's important to understand here is that in order for the charges to pass through the aqueous solution, the medium, the ions must be present. So in other words, the reason why there's a lot of, this light bulb is shining very brightly is because there are a lot of ions in this beaker, in the solution that's made up in this beaker. Vice versa, when you have something where the light bulb doesn't turn on at all, that means that even though the solution, the solute is dissolved in water, it doesn't produce any ions, okay? And that's really the basis of the way we differentiate among different types of solution. So if you go to the next slide, it tells you here the different types of solution based on relative electrical conductance, which means just that which one conducts a lot of electricity versus a little bit versus nothing. The types of solutions that can conduct electricity very strongly are what we refer to as strong electrolytes. What that means is usually that the solute, when you put it in water, when you dissolve it, it produces ions 100%. In other words, if you start with, let's say, 100 particles of sodium chloride, basically all those 100 particles would break apart into 100 sodium ions and 100 chloride ions. So in other words, 100% dissociated into ions, okay? The type of compounds that do this are strong acids and strong bases and soluble salts. And we'll give a few examples of this in the next slide. The next type of solution is what we call weak electrolytes. Those are solutions that earlier were shown in the middle with that light bulb that's kind of weakly shining, but not, obviously not a lot of electricity, which implies that there's not a lot of ions that's produced by those solutions. So the type of compounds that belong in this weak electrolyte category are weak acids and bases and things we call insoluble salts, which really I put a quotation mark here because a lot of times these salts are a little bit soluble, and that's why they can conduct electricity. They are soluble a little bit, but in comparison to something like sodium chloride, these salts are pretty much insoluble. Okay, so only a small portion of it is soluble. So you can think of it, earlier I was giving you an example of 100 formula units of sodium chloride, you'll get 100 cations and 100 anions. For something like this, if you have 100 formula units of something like silver chloride, for example, which is an example of an insoluble salt, you might get one or even less than that. If you have 1,000 particles of this silver chloride, you might get one of it that actually goes to form an ion, whereas the rest of them just clumps together into that silver chloride structure. Okay, so it doesn't, in other words, it doesn't get broken apart by water, or only very little of it. And then of course you have non-electrolytes. These are basically things that dissolve, but they don't conduct electricity. Okay, so the stuff that belong in this category are all your polar covalent compounds. So earlier we gave an example of methanol being an example of a polar compound, or sugar, that both of them are examples of polar covalent compounds that dissolve in water. Neither one of those solutions will conduct electricity when you do an experiment like the one I showed earlier. Okay, so let's take a look at the various examples of these strong electrolytes, weak electrolytes, and non-electrolytes. So this is a table that basically shows you some examples of these guys. So things that belong in the strong acid column are all of these species. We'll talk a little bit more about them when we get to the acid-base part of this chapter. Strong bases are all of these guys, the hydroxides of group 1A elements, meaning sodium hydroxide, potassium hydroxide, lithium hydroxide, and so on. Hydroxides of calcium, barium, and strontium. They tend to be, they're strong bases, but they're usually also, the solubility is fairly low. And then you have soluble salts. These are things that just, dissolve in water very easily in a large amount. So these are some examples of them. We'll talk more about them in a second. Weak acids, these are the examples of some of the weak acids that you want to keep in mind. Weak bases, ammonia is the main one that you really want to remember, NH3. And then there's also some other weak bases that you might come into contact with in this class. Derivatives of ammonia, for example, methyl ammonia, ethyl ammonia, and dimethyl ammonia, and so on. Okay, and then you also have insoluble salts. Again, these are salts that don't dissolve too much in water. They're ionic compounds, but they don't dissolve. They don't produce a lot of ions in water. We'll talk a little bit more about them in a second also. And then of course you have your polar covalent compounds, things like methanol, ethanol, glucose, table sugar, sucrose, and so on. Okay. I want to highlight here that you want to memorize this list, i.e. you want to have an idea of what these compounds are, especially the weak acid, weak base, strong acid, strong base, because at this point this is really your guide for what would be a strong electrolyte, what would be strong acid, strong base, and what would be weak acid, weak base. The soluble salts, insoluble, you also have to memorize what their rules are. We're going to talk about in a second how to know them. And the covalent compounds are usually fairly obvious as well. Okay, so here is the solubility of a salt. And what I'm going to do is actually stop the video here and continue in the next video, because this is going to be related right away with the concept that we're going to talk about last, which is the idea of the different types of equations we can write. So keep this slide in mind, because I'm going to start with this one in the next video.